So, we'll be back from the break, dear viewers, my students tonight. I'm very delighted to have you tonight. So, we are still continuing. We stopped on the SI unit of velocity, which we talked about as meters per second. Now, what I want you to note is that velocity has other units, or speed has other units. So, we can note and say that the other units of speed and velocity are, or is, we can talk in terms of is, a unit. So the other unit of speed and velocity is kilometer per hour. So this is kilometer, small k, small m, then per hour. Or we can write it as kilometer power -1. So that is the unit. We also have miles per hour. Yes, you'll see on some gauges of different machines, moving machines, you'll find miles per hour. But for us, we are going to concentrate on a kilometer per hour. Now let us go and see how can we convert to SI units. Converting to SI units, because this gives students difficulties. If speed or velocity is given in kilometers per hour, students cannot convert to SI units. So converting to SI units is our small subtopic. And this takes us to an example, and from there we shall get an exercise for you. Okay, so my example, let me divide my board, and then example 1. So someone can tell you to convert, for example, 108 kilometers per hour to meters per second. That can be an example. So example 1. Convert 108 kilometers per hour to meters per second. You should be having a scientific calculator. My calculator is here. This is my calculator. So this is very simple. Kilometers per hour, it means distance over time. Convert the distance to meters, then convert the time to hours. Yes, we know very well in our solution. This is the solution. Note, in this solution of ours, we need to note that 1 kilometer, small k, small m, not capital K, not that. So 1 kilometer, okay, is equivalent to 100 meters. 1 kilometer is equivalent to 1,000. Actually, it will be 1,000 meters. Yes, that is true. Somebody has advised me. So, if that is very true, then we can go ahead. What about 1 hour? 1 hour is the same as 60 times 60. 60 times 60 seconds. And this is the same as 3,600 seconds. This is very true. So after noting this down, then there is no way you can fail to convert this. Because you get to know that if I'm converting 108 kilometers, these kilometers, converting them to meters, I'll multiply through by 1,000. Then this 1 hour, converting it to seconds, from a larger unit to a smaller unit, then which means the seconds will be many. You will multiply it through by 3,600. So we come here and say the speed, 108, this implies that 108 kilometers per hour, that is distance over time. Get the distance, 108 and kilometers, multiply them through by 1,000, Then get the hour, which is 1 times 60 times 60, which is 3,600. So if you put that onto a computer or into calculation, I'm seeing it is bringing, even if we don't use a calculator, 2 zeros cancel, 1080 over 36, that is 30. So we are getting 30 meters per second. So the answer is 30 meters per second. Another person here would have used this method. Yes, I want you to first copy this, and I give you a different alternative method. You can get my clear posture. You pause the video if you are watching this as a recorded video. If you are watching us live, then you can print the screen, paste it into any document. Press Ctrl key on your keyboard, and then the print screen key on your keyboard. Then you would have copied what is on your screen. Then paste it in a Word document. You can open a new Word document. Yeah, open a new Word document, paste there, then you'll find this work there as an image. So let us go and see another method of doing this. Method 2 of doing this. So, or alternatively, this is what we could go. 108 kilometers in every hour, in every 1 hour. That's what it means. So the distance is given, and this is speed or velocity. So from speed, which is equal to distance over time, or we would have used the velocity, displacement, or distance moved in the specific direction over time. See, we shall come to the same formula. So the distance here is given. Distance is given as 108 kilometers per hour. But we know very well, we can start from the known to the unknown. What is the known? We know the equivalence of a meter to an hour. We are converting from kilometers to meters. So kilometer first to meter. So we know the word that 1 kilometer, Mr. Examiner, sir, is equivalent to 1,000 meters. What about the 108 kilometers for this distance? Will be equivalent to, we cross multiply. Or you can put an unknown x. Cross multiply, make it the subject of the formula. But for people who have done some chemistry, the more concept, you know what to do with first principles. You don't need to put an unknown, just cross multiply, divide through by the first item or element. So this is the same as 108 times 1,000 over the first element, which is 1. And this will give you 108,000. These are now meters. So you have converted the distance. That is the distance. Then come and convert the time. The time is given in hours. So start from the known to unknown. We are converting to a second. We know very well that 1 hour, so tell the exam that also 1 hour is equivalent to 60 times 60 seconds. But we know 6 times 60, 36, and then the 2 zeros, giving you a 3,600 as a value for those seconds, equivalent to 1 hour. Very interesting. What about 1 hour here? Automatically it is the 1 hour. We are talking about per hour, every hour. That is the meaning of the slash, every hour. So it is the 1 hour. We have converted it already. And we have got 3600 seconds. That is the equivalency of 1 hour. Therefore. So let us go and calculate our speed. So this implies that, Mr. Examiner, sir, our speed is now going to be the distance. What was the distance? The distance is 108,000. Divide through by the time. What is the time? The time is 3600. Very interesting. So from here, we can calculate. So these zeros will go, can cross out these 2 zeros, okay? And then we say by maybe, somebody can say by 18, or by 9, or by 36. By 36 once, by 36 3. Because 36 times 3, we shall get 108. 8. So plus this 0, we shall get a 30. So therefore, our speed, but what was this speed? The speed was 108 kilometers per hour, is equivalent to 30 meters. You've got this in meters, you are dividing it by time, which is in seconds, so meters per second. So this is the correct answer. So always the physics is very simple, my dears. Very, very, very simple. So hope now we can go to another example. Let's rub off and go to another example. So example 2 is here. The examiner is telling you to convert. So you can believe or you will agree that method 1 was very, very short and precise and very easy. It was very, very easy. So assuming now somebody tells you maybe to convert a value like where is my marker? Convert 216, okay? Yeah, kilometers per hour to meters per second. So still the same. I don't expect you to use method 2. However much method 2 makes you understand this best and more. So 2116, yes, we come here and say that the 2116 is equal to 2116, convert the kilometers to meters by multiplying through by 1,000, then every hour, then the hour, bring it, and yes, multiply it through by 300, 600. So when you divide this, I'm saying by 36 once, 216 from your calculators, divide through, because these zeros, they go on cancelling. So I'm seeing a 6 here. It is going to be a 6. If I add 108 times 2, it is going to bring out a 6. Oh, I mean, yeah. Okay, and 2 times 3, it is going to bring out a 60. So the answer here is 60 for those who can use their brains. If you can't use your brains, then you can use a calculator as an assistant to your brains. So before we go for the 5th term, remember we are still on the 4th term, use the under motion. And that is a term of velocity. However, they share units with speed. That's why we have gone on to a calculation. I want to give you some not even homework, just a break assignment. I want you to go and try for me these numbers. Oh, very interesting. So the first question is here. So this is assignment or trial. It is here for you for this short break we are going for. So trial. Okay. Now assume somebody tells you that maybe a vehicle moved 120 kilometers in a time, you say 3 hours. Then what is the vehicle's average speed? That can be a good question. Yes. So a vehicle, that is number 1. A vehicle moves, or you can say it moved, or it travels, or it covered, but I think covered is very, very okay. So a vehicle, not vehicles, but vehicle, covered 120 kilometers in 3 hours. So part A, average speed. What is the vehicle's average speed? Very simple question. What is the vehicle's average speed? So remember we talked about calculation of average speed. If you can't recall, then there will be a problem. Then what if again I ask you, what distance yes will be covered by the vehicle by the vehicle in, say, okay, let me give you 90 minutes. In 90 minutes. That is 1 hour and 30. 1 hour and 30 minutes. 1.5 hours. Yeah, in 90 minutes. Let me give you that. Very interesting question. That is number 1. Let me also give you number 2. I'll stop on number 2. So number 2 is going to be very simple. So assuming now I give you a conversion. This time around I'm going to give you even converting from meters per second to kilometers per hour. So number 2, convert. Part A, 72 kilometers per hour to meters per second. Not kilometers per hour to meters per second. Then part B, assuming I have 30 meters per second to kilometers per hour. Not meters per second to kilometers per hour. Immediately after this short break, when you have completed your exercise, we are moving to the 5th term of our concept of motion, and that is uniform velocity. You want to see velocity in details, uniform velocity. Then we shall also talk about uniform speed as the 6th term. So, I wish you the best in trying out those numbers. Stay tuned. Welcome back from the break, dear viewers. We have now moved to term number 5, that is uniform velocity. So, dear viewers, what is uniform velocity? What is the meaning of the word uniform? Oh, same. That is the same. Oh, take a look at this. Assuming I have a vehicle or a body which is moving, its velocity, its distance is changing with the time. At maybe a time t is equal to 2, that's where we started timing it. At a time t is equal to 2, then the distance covered. This is distance covered in meters, time in seconds. Assuming the distance covered here is 4. Oh, very nice. When the time now moves to 4, the distance covered here, assuming it is 8. When time moves to 6, oh, the distance covered here is maybe 12. And when the time moves to maybe 8, the distance covered here is 16. Now the question is, can we go and calculate the speed? So speed in meters per second for every journey. Yeah? Assuming here at point A, at point B, at point C, at point D. Let us go and see the implication of the speed. So, speed is equal to distance over time. So, 4 divided by 2, what do we get? Oh, wonderful, we get 2. 8 divided by 4, what do we get? Oh, that is correct, it is a 2. 12 divided by 6, what do we get? Still a 2, marvelous. 16 divided by 8, what do we get? A uniform value, the same value. Like a uniform you put on, you are putting on the same attire, something of the same color. It is the same throughout. The same applies here. So, when there is a constant time rate of change of distance, then we say a body is moving with uniform speed. If this is not distance only, but it is displacement, then a body is moving with uniform velocity, because velocity is in line with displacement. It is uniform speed or uniform velocity. It is the same. So a body's time is changing by equal magnitude. Look at the change from A to B. Look at the change in time. 4 minus 2, it changed by 2. The time is changing by 2. From B to C, look at the time change. The time changed from 4 to 6. The difference there is 2. From C to D, the time change is 8 minus 6, which is also 2. Let us also go and look at the change in distance. So the change in distance or displacement from 4 to 8, there is a change of 4. So here there is a change of 4. Then from 8 to 12, there is also a change of 4, that is B to C. From C to D, that is 12 to 16, there is a change of 4. So a body's displacement is changing, or they are changing by equal magnitude in equal time intervals. So in other words, somebody can define uniform velocity as a phenomenon or a situation when a body's velocity, or this is when a body covers a velocity in a changing equal magnitude in equal time intervals. Have you seen that? Just by illustration. But for us here, we can say that uniform velocity is, I need to use a black. So this is the time rate of change, a constant time rate of change. It has to be constant. This is a constant time rate of change of displacement. Or this is when a body's displacement changes by equal magnitudes in equal time intervals. Very good. That's what we call uniform velocity. So it is the same thing as uniform speed. Where there is displacement, we shall just put the distance. Hope you can get that. So that takes us to term number 6. That is uniform speed. Uniform speed. So uniform speed, this is a constant time rate of change of distance. We are going to talk about time and then distance. Those are the two terms. Or uniform speed is when a body's distance changes by equal magnitudes in equal time intervals. Okay? The body's distance is changing by equal magnitudes. For example, here by 4 by 4 in equal time intervals. That's what we call uniform speed. Now, let us go and look at something very interesting. That is term number 7, what we call acceleration. Can everybody say acceleration? Acceleration. Let me put it here, aside it. Acceleration. That is term number 6. I'm seeing people are getting exhausted. Don't get exhausted. We are on a very important aspect here, and that is acceleration. So, dear viewers, what is acceleration? Pronounce this as acceleration. C-E-L-E-R-A-T-I-O-N. Acceleration. What is to accelerate? Oh, somebody is saying when the speed increases in a given direction with increase in time. That is correct. So acceleration is going to be defined as the rate of change of velocity with time. So this is the rate of change of velocity with time. The velocity is changing with time. Or another person can say that acceleration, yes, can you give me a different definition? The time rate of change of velocity. Yes, it is the same, just reversing these words. I want you to use speed. Yes, the time rate of change of speed in a specific direction. That when you use a scalar quantity, try to make it vector by putting its direction. Wonderful. So acceleration is the time rate of change. Is the time rate of change of speed in a given direction. In a given direction. Wonderful. Very, very wonderful. So by definition, we are going to see that since acceleration involves change in velocity, assuming a body starts with a velocity u, that is starting velocity, and as it traverses or it moves, the velocity increases, goes to a maximum value, for example v, then there will be a velocity change as the time is elapsing. So we can go and define acceleration mathematically as change in velocity over time taken. Change in velocity over time taken. At this level, I expect you to be having a revision book of definitions only. Yes, to master them. So mathematically, acceleration A is equal to change in velocity over time taken, or over change in time. So if a body starts with a velocity u and attains or it acquires a velocity v after a time t, then acceleration is change in velocity, final velocity minus initial velocity over time taken. Is it okay? U is equal to starting velocity. To start is the initial position, so we call it initial velocity. Then V is the final velocity. Then T is the time taken. Time taken for the velocity to change. So what else do we need to note about acceleration apart from the definition and knowing that acceleration is given by this mathematical formula? This mathematical formula will produce what we call the first equation of motion if we make V the subject of the formula by cross multiplication. So acceleration, I'm donating it with small a, so it is not capital A. Those who are putting capital A, you are wrong. Okay? So let us go and see other facts about this acceleration. this acceleration. So another fact about acceleration, its units are so unique. We are getting the units of velocity divided by units of time. Velocity was already in meters per second divided by time, which means a second is going to appear now many times. So SI unit of acceleration is meter. SI unit of acceleration is meter per squared second or per square second. So how do we write that? Meters per square second or meters per square second in terms of an index. So how do we come to this? By laws of indices, just like the way we proved the units of velocity. So this is acceleration, my dear viewers. So after noting the SI unit of acceleration, we can still go and note about whether acceleration is a vector quantity or scalar quantity. According to you, what do you think? Is this a scalar quantity or a vector quantity? Well, people are saying vector. Reason being, it contains velocity. Which velocity is given by displacement? Which displacement is a vector quantity? So acceleration is a vector quantity. Acceleration is a vector. What? Is a vector quantity. Very, very wonderful. Very, very marvelous. So immediately after a break, after you memorizing the whole of the concept of acceleration, I'm coming back with the 8th term, and this term is what we call uniform acceleration. Uniform acceleration. Let me find you with the definition of uniform acceleration after borrowing a leaf from the definitions of uniform speed and uniform velocity. Teacher Sulait is coming back after a break. Stay tuned. I'll be back from the break. Hope you have made research about uniform acceleration. Now with acceleration, we are varying velocity with time. If you remember a table which I drew for you here, which was for time and distance. Where there is distance or displacement, you put velocity. And then the values which you calculate, those two, let them be for acceleration. Hope you are going to rewind and then see the table I'm talking about. So that is what we call uniform acceleration. The body's velocity is changing by equal magnitude in equal time intervals. The body's velocity is changing by equal magnitude in equal time intervals. So this gives a constant rate of change of velocity moved with time. Constant rate of change of velocity covered with time or velocity attained with time. That's what we call uniform acceleration. So we can define it and say that this is the uniform rate of change of velocity. Oh, not uniform. We can use the word constant because uniform has already been used. So this is the constant, something which is not changing. This is the constant. Oh, this is the constant rate of change of velocity with time. That is uniform acceleration. Now, in motion, if a body starts from rest, once you hear the word rest, then a body has started from with a velocity of 0. So remember we said initial velocity or starting velocity is noted by u from the definition of acceleration. So we need to note that. Take that note. Note. In motion, when a body is a general term for any object. Make it a car, make it a vehicle, a bike, make it a human being, make it an airplane, make it a baby bird, which is describing motion, unsquared baby sheets, anything. So in motion, when a body starts from rest, then initial velocity, then starting velocity is zero, i.e. u is equal to zero. That is very true. You also need to note, these are some of the words we are going to be using in our calculations, which means we are now moving to calculation. We want to see how to calculate uniform acceleration using our formula, change in velocity over time. If a body is brought to rest, a body has been moving, it started with a velocity u, and then finally settles the way I've now stopped moving. It means my ending velocity, or what we call the final velocity, has been brought to rest. So rest does not always refer to starting only, but you can also come to rest. Final velocity can be zero. So in other words, so we can say, and when a body is brought to rest,